Good morning. All right, so we're going to finish up this last example in section 2.5, and then we'll get into 2.6 today. Right now, it shows that the homework is due tomorrow night. That won't happen, obviously, because we haven't gotten through all of 2.8 yet. So I will move that into next week. Probably middle of next week is what I'm looking at. We'll kind of play it by ear, but I'll at least move it, into next week, and then keep pushing it back until we actually get through all of chapter 2. Now, we should finish up chapter 2 by the end of next week. That's kind of my goal. Which means then that the following Monday would probably be a review day, and then we should have the test that following week, right? So not next week, but the following week, be expecting the test on chapter 2, okay? Any questions, comments, concerns before we get started today? All right. So we had started this problem yesterday, right? And so we were looking at John and Mary, and these graphs represent basically how far they've traveled over a certain amount of time. And so we were able to use the slope of each of these lines to find their speeds that they were actually traveling, right? And then we talked about the fact that just looking at the graph, we know that Mary's traveling faster because her line is steeper than John's, right? And so that's what we stopped with yesterday. Now we actually want to find the functions for each one of these lines that would model how far each of them has traveled, right? So let's start with John in this case. Let's see if we can come up with a function to actually model his distance traveled over time now. Give me 1 second. My pen's not writing. There we go. All right. So if we want to find a function that models John's behavior this time, right? So let's think about what we know in this case. So our x-axis represents the number of hours. We know the y-axis represents the miles that have been traveled, right? So how could we write a function here to model his distance traveled over time? What's the form of the equation going to actually be this time? So we have the slope for John's equation, right? But we don't have the entire equation yet. Good, Destry. So we want this in the form y equals mx plus b because we actually have a linear function this time. We know the slope, right? We already calculated that. So what's the only other thing we're missing in this case? Okay, we need the y-intercept, right? And so if we look, we can actually get that from the graph. So if you look over here now, John's line intersects the y-axis right here. That is 150. And so we can say that his function is going to be y equals 50x, right? Because 50 was our slope, plus 150. Okay, so when it's asking for the actual function here, we're looking for that linear function to model that line. And so that's going to be y equals 50x plus 150. Any questions about how we got that line? All right, let's look at Mary now. So what would the equation for Mary's line look like? Good, just y equals 75x, because notice here, her y-intercept is 0, and so we don't really need anything for the b value, so we're just going to have y equals 75x. Again, that 75 just comes from the fact that her slope was 75, and so we get y equals 75x. Any questions on getting either one of those equations now? All right, so now we want to actually use those equations to answer these last two questions. So we want to say, how far will John and Mary have traveled at 5 p.m.? So how are we going to figure out how far John would have traveled at 5 p.m.? Good, right? So we know in this case that our x values represent a number of hours, 0 represents noon, and so 5 p.m. would be an x value of 5. So we're going to take x equals 5, and we're going to do what with it? Plug it into both equations, right? So we want to find John's distance and Mary's distance. So we're going to plug 5 in. I'm going to go to the next slide just so I have room to actually write this out. And so we started with John here. His equation was y equals 50x plus 150. So I'm substituting 5 in for x. So we have y equals 50 times 5 plus 150. And so what's that going to give us for his distance if we simplify that now? 400. Good. Right. So this is 400, and the units we do need, and those are measured in miles now. So at 5 p.m., John would have traveled 400 miles. Now let's look for Mary. Mary's equation was y equals 75x. Again, we're using that same 5 o'clock, so that's 75 times 5. And so how far would Mary have traveled? 375 miles. Good. All right, so that answers that question, right? So now at 5 o'clock, we know how far each one of them had traveled. Any questions about those two questions? All right, now the last part here says, for what time period is Mary behind John? Will Mary overtake John? And if so, at what time? So I really just want to know, first off, is she going to overtake him at some point? Yeah, right. She's traveling faster. Eventually, she's going to catch him, right? So now the question is, at what time will that happen? How could we figure out when she would catch John? Okay, so we could look at the graph, right? So we could graph both of these and extend our window out and figure out where they actually intersect. What's another way we could do it algebraically without actually looking at the graph? Good. Just set the two equations equal to each other, because that would be the same thing as finding where they cross each other, where they intersect. So what I'm going to do is I'm going to take John's equation and Mary's equation now, and I'm just going to set them equal to each other. And what I mean by that is just the 50x plus 150 part. I'm going to set it equal to the 75x, right? Because that represents John's distance being equal to Mary's distance now. Now, how would I solve that? Okay, subtract the 50x, good. When we do that, that's going to give us 150 is equal to 25x. And then we can do what? Good. If we divide by 25, what's our x value going to be this time? Okay, good. Now, what are the units going to be here? What does that x value represent? Hours, right? Okay, and so in this case, our x is going to be 6 hours. Or if you want to think about the specific time, what time would that be? 6 o'clock p.m., right? We know we started at noon, and so 6 hours after that would be 6 o'clock p.m. That's when she would actually catch him. Any questions about how we found that now? And again, what Matthew said is completely correct, right? We could have also just put this in Desmos or a graphing calculator, expanded out our window, and then look for where those two lines intersect each other. And whatever that x value is going to be the answer to this problem, right? It should also be x equals 6 if you were to find that point of intersection. All right. So that's it for that section now. So let's move on to 2.6. All right, so 2.6 now is transformations of functions. So what we're going to look at here is using some of the things we know about our basic functions, right? Because we know what a basic x squared function looks like now. We know what a basic square root function looks like now. We're going to look at how we can take those basic functions and then actually move them around, make them bigger or smaller, those types of things. Okay, so that's what the transformations are going to do. All right, now, the first type of transformation we're going to look at is what we call a vertical shift. So if we have a c value that's greater than 0, meaning we have a positive c value, and we add that to a function. So notice here we're taking the entire function and we're adding c to the outside. What that's going to do is it's going to take the original f of x graph and it's going to shift it up c units. So if we know what the original f of x would look like, then we can just say, well, if we're adding c to it, it's just going to move that original graph up that many units now. And on the other hand, if we subtract c instead, again, on the outside of the function, then it's going to move it down that many units. And we can see that in the graph over here. The blue graph is the original, okay, so that's our f of x. And so if we add a positive c value to it, it's going to shift it up and give us that red graph. And if instead we subtract the c value, it's going to shift it down and give us the red graph here on the right-hand side. Any questions on the vertical shifts? We're going to look at examples of how we actually do this, right? But any questions for right now? All right, so let's take a look at this example. So we're going to use the graph of f of x equals x squared. This is what we would call a parent function because it's something we already know what it looks like, and we can use it to help us sketch these transformations now. So we're going to try to sketch the graph of x squared plus 3 using what we know about the graph of x squared. So let's start with our x squared graph. What does x squared look like? Okay, it's a U-shaped graph, right? So we call that a parabola. Where is the vertex going to be for that parabola? At the origin, good. So at 0, 0. And which direction is that parabola going to open? Up, right? We have a positive x squared in this case. So we have a parabola that opens upward, looks something like that. Okay? So that's just one of those functions that we need to know. As soon as you see x squared, that's what the basic graph is going to look like. Now we want to apply our transformations to that graph. So if we look at g of x, we have x squared plus 3. What is that going to do to our graph now? It's going to move it up 3 units, right? So we're going to have a shift up 3 units. So all I need to do now is take that original parent function, the x squared, and shift the entire thing up 3 units. My g of x. Where are we actually going to start this time then? Where would that vertex be? At 0, 3. Good. So we're going to move it up 3 units on the y-axis. We're going to have a point right here now. Notice nothing else has changed, so it's still going to be that parabola. It's still going to open upward, and so it's going to look something like this now. But the whole thing is shifted up 3 units from the origin now. Any questions about how we got that graph? Now, keep in mind, right, you have access to Desmos. You can use a graphing calculator if you want. So I'm not going to ask you to actually graph these things because I know you can just put them in a calculator and figure it out. I'm going to ask for the verbal description in words, right? So those are the things I'm going to ask for on a test is, hey, describe what types of transformations are happening with this equation now. And so you have to recognize the plus 3. It's going to shift it up 3 units. All right, so let's look at the second one now, h of x. So again, x squared is still the parent function. What type of transformation are we going to have this time? It's going to go down, right? So because of the minus 2 now, it's going to shift down 2 units. Okay. So again, that's what I would ask for on a test, right? Is the actual verbal description of what type of transformation we have. So in that case, make sure you tell me if they shift, right? Because that's the first piece. Make sure you tell me which direction it's shifting, and then make sure you tell me how far it's shifting. All right, so if we do that for this graph now, what's that going to look like? Good. We start at 0, -2, right? Because we're shifting down from the origin 2 units. Which way is our parabola going to open? Still up, right? So be careful. A lot of people like to flip it at that point or something. We only shifted it down to everything else about it stays the same. And so this is still going to look just like this now. Any questions about how we got that graph? All right, so those are vertical shifts. The next thing we have what we call horizontal shifts, right? So vertical is up and down. Horizontal now is going to be left and right. So if instead of having a plus or a minus c value on the outside of the function, this time we're adding or subtracting c on the inside of the function, right? So it's going to actually be grouped with the x in this case. If we subtract a c value, it's actually going to shift the graph to the right c units. Now that might be backwards from what you would expect to happen, right? Because you would think, oh, well, it's a negative c, right? It seems like that would move it to the left. It's backwards, okay? So just keep in mind a minus c is always going to move it right that many units. And then a plus c on the inside is actually going to shift it to the left that many units instead. In general, the stuff on the inside of a function is going to be backwards from what you would expect, so just keep that in mind, okay? So that's with addition, subtraction, and the multiplication we're going to look at later. Okay, the inside stuff is always backwards. And we can see that in the graphs down here. Again, the blue is the original function now. If we subtract a c value from that, it's going to shift it to the right and give us that red graph we have on the left. And then if instead we add a c value to that blue graph, it's going to shift it to the left that many units. And so we would get that second graph instead. Any questions on the horizontal shifts? All right, so let's practice that. So again, we're using x squared as our parent function. We know what that looks like. We want to sketch the graph of g of x equals x plus 4 all squared. So the first thing we want to do is just verbally describe what's going on here, right? So what type of transformation are we going to have? Good. It's going to be a shift to the left 4 units. Again, the way we know it's either left or right is because the plus 4 is on the inside. Because it's a positive 4 this time, that's what moves it to the left. And then always include how many units you're actually shifting it. Any questions about how we got that shift now? All right, let's sketch that graph then. And our parent function is still x squared. So where's our vertex going to be this time? Okay, so x squared would have been at 0, 0, but now if we shift it to the left 4 units, where is it going to be? At negative 4, 0. Good. We're going to move it left along the x-axis then. There's our vertex. Again, nothing else has changed here, right? So it's still going to be a parabola that opens up. We're going to have a parabola that looks something like this now. Any questions on that one? Okay, let's look at h of x. So what type of transformation are we going to have for h of x? Good. This time we're going to have another shift. Because it's inside, we know it's horizontal, and a minus is going to shift it to the right. 2 units. So then again, we're going to sketch that graph. Still basing it off the x squared graph this time. So where's our vertex going to end up if we shift to the right 2 units? At 2, 0. Good. Positive 2 on the x-axis puts us right here. And then again, it's just going to open upward. Get something like this. Right? And again, these are rough sketches. I don't really care about the y-intercept or anything like that. Okay, so as long as you got the vertex in the right place, basic shape of the graph correct, right? That's what I'm looking for there. And again, on the test, all I'm really going to be looking for is that verbal description. Any questions on the horizontal shifts now? All right. So let's see if we can put some things together now. So this time we've got square root of x minus 3 plus 4. First thing we've got to do is identify what is the parent function, because they're not telling us what that is this time. What's our parent function going to be? Square root of x. Good. So we're graphing y equals square root of x as our parent. So let's think about what that graph looks like first, and then we'll think about what transformations we have. So what do we know about the square root of function? So you're basically looking for what are you doing to your x values, right? So in this case, like the last ones, we were always squaring everything. In this case, we're taking the square root of the x, right? So that tells us that we have a square root of x as our parent function. If we had something like, x plus 3 to the third power, then x cubed would be our parent function. Does that make sense? Okay. Yeah, and so always just find what's the most basic thing I could break this down into, right? to be able to just add, subtract, and multiply something to the x and be able to transform it. Okay, so in this case, square root of x is that most basic function. Now, what do we know about the square root of x this time? What do we know about that graph? Okay, it goes up and to the right, and we start where? At the origin. Good. So we're going to start at 0, 0. It's going to open up and to the right. It levels out and curves out like that. Okay. So that's our basic square root of x function. Now, what types of transformations are we going to have this time? Okay, both horizontal and vertical. Good. So let's look first at the horizontal. What type of horizontal transformation are we going to have? What's it going to do? It's going to move to the right 3 units. Good. So that minus 3, because it's grouped with the x, right? Even though there's no parentheses there, it's still under the square root with the x. We consider that inside the function. So this is going to be a shift to the right 3 units. Okay. What other type of transformation do we have then? Or what is the other transformation? It's going to go up 4 units. Perfect. So shift up 4 units. So we have both a horizontal and a vertical shift this time. Now let's think about what this graph is actually going to look like. I'm graphing f of x now. Where is my starting point going to be? 3, 4. Good. So we're shifting to the right 3 units. We're shifting up 4 units. And so we're actually starting here at 3, 4 now. Again, those are the only transformations that are happening. So it's still going to look like that parent function. It's going to open up and to the right, just starting from that point now. So it's going to go up and to the right like this. And that's what our graph would look like. And again, right, you have access to Desmos or a graphing calculator. You can always put this in there just to double check yourself, right? But again, I need you to know how to list out what those transformations are. Okay, but use the graph if it helps you. But understand, we need to be able to look at the actual function and just pull out those transformations. Any questions there now? All right. Now, the next type of transformation is what we call reflection. So if we put a negative in front of our function, it's going to reflect the graph over the x-axis. Okay, so notice here the negative is in front of the entire function. That gives us a reflection over the x-axis. If instead we put a negative value inside the function, so it's grouped inside with the x now, that's still going to give us a reflection, but now that reflection is going to be over the y-axis instead. We can see that in the graphs at the bottom here. So again, the blue is always the original. If I put a negative out front, that gives us a reflection over the x-axis. So that first graph on the left there shows us what that reflection would look like. And then if we have a negative on the inside instead, that's going to give us that reflection over the y-axis. And we can see that in that second graph. Any questions about the reflections now? That's right. So when you describe it in words, you would say it's a reflection over and then whichever axis. Okay. All right, so let's take a look at these now. So again, first thing we have to do is identify what's the parent function, then we'll identify the transformation, and then we'll actually sketch the graph. So for f of x equals negative x squared, what's our parent function going to be this time? just x squared. Good. So y equals x squared is the parent function. Now, what type of transformation are we going to have for this f of x function then? Okay, so it's going to be a reflection. So now the question is that negative inside with the x, or is it in front of the entire function? So tell me that first. Is this inside with the x or in front of the entire function? It's in front of the entire function, right? So if we go back and we look here, when it's in front of the entire function like that, that's actually going to give us a reflection over which axis? The x. Good. So this should actually be a reflection over the x-axis. And again, it's because that negative value, it's not grouped with the x, right? It's not inside. It's actually in front of the entire x squared, and that's why we get a reflection over the x-axis. Any questions about how I got that now? That's right. Okay, so if you wanted a reflection over the y-axis, then you would need parentheses around the negative x, and the entire negative x would be raised to the second power in that case. Okay? All right, so now let's think about this graph. So what would our graph look like then if we take our parent function and reflect it over the x-axis? Good. It's just going to open down, right? So in this case, we're still going to start at the origin. That point's not going to change. But now instead of having a parabola that opens up, we're going to have a parabola that opens down instead. And so that would be our graph of negative x squared. Questions on that one? Okay, let's look at the second one. So same thing, I want to first identify the parent function. What's my parent function this time? Square root of x. Good. So y equals square root of x. So in this case, what type of transformation are we going to have? Good. This time it's a reflection over the y-axis. And the way we know that is that negative is inside the function with the x. So reflection over the y-axis. Right? That negative is not in front of the entire square root of x. It's only on the inside with the x this time. Okay, so if we think about that graph, what's that going to look like then if we reflect the square root of x function over the y-axis? Good. This time it's going to open up and to the left instead. So we're still starting from the origin. But now instead of going up and to the right, it's going to go up and to the left. And so we're going to have something like this now. Any questions on that one? Or any questions on any of the reflections now? So we have to keep in mind in this case, right? The reason it does this is because now my x values for this graph are all negative values, right? And so let's say, I have take a negative x value here, like -4. If I substitute it in the function, it's going to be y equals the square root of -4. And so -4 would actually become what? A +4. And when we take the square root of 4, that just gives us 2, right? So that's why this works, is because now the negative x values, it becomes a double negative because all of our x values are negative anyway. And so they all become positive, and we can actually take the square roots of those values now. Okay. If the negative was outside, it would reflect over the x-axis instead, right? So if this had been negative square root of x, this would be a reflection over the x-axis. Because in that case, the negative's in front of the entire function, right? And so that would give us that reflection over the x. Okay. All right, and then Destry, does that answer your question about why the negative doesn't make it imaginary? Okay. So since x is still a variable, right, okay, we can actually put negative values in for x, and so then they actually become positive with the double negative. Any other questions here? All right. Stretching and shrinking. And we're going to start with vertical here. So if we have a function where we have a c value multiplied in front of the entire function, if that c value is bigger than 1, then we're going to have what we call a vertical stretch by a factor of c. So again, if that c value is in front of the entire function and that c value is greater than 1, then we have a vertical stretch by that factor. If instead we have a c value that's between 0 and 1, so in this case, think like it's going to be a fraction or a decimal value, right? If it's between 0 and 1, then we're going to have a vertical shrink by that factor of c instead. So again, as long as the c value is out front, it's always going to be vertical. If the c value is bigger than 1, it's a stretch. If the c value is between 0 and 1, then it's a shrink. You can see in the graphs down here what that would look like. The blue graph again is the original. If I stretch that thing vertically by a factor of c, that's going to give us something that looks like the red graph. Notice the x values haven't changed here. It's only those y values that are getting stretched out. That's how we get a vertical stretch. And then with the other graph now, if that c value is between 0 and 1, again, the blue graph is the original. I'm going to shrink that thing vertically. That gives us the red graph that we see on the right-hand side there. Any questions about the vertical stretches and shrinks? Okay, let's take a look here. So again, we're using the parent function x squared. I'm going to describe what type of transformation we've got, and then we'll sketch the graph. So what type of transformation would we have for 3x squared this time? It's going to be a stretch. What type of stretch is it going to be? Correction, vertical, right? So we have to indicate that it is a vertical stretch. And then we always want to say by what factor. So it's by a factor of what? 3, good. So the verbal description of that, right, we have to say that it's vertical, we have to say that it's a stretch because it's bigger than 1, and then we say that it's by a factor of 3. Now, I'm not going to actually sketch this one. The vertical stretches and shrinks are just really difficult without actually putting specific points on there. Just know that you're going to take your parabola now, you're going to stretch it like taffy vertically, right? And so it just becomes kind of a more narrow parabola that's opening upward. But again, if you want to put it in Desmos and look at that, you can see it. But again, on the test, I'm not going to ask you to actually graph these transformations. I'm just going to ask you to describe them. So as long as you can tell me that's a vertical stretch by a factor of 3, that's what I need to know. Okay? And what about h of x? What type of transformation is that going to be? Vertical shrink. Good. So numbers out front, right? So it's still vertical. But now we have a value that's between 0 and 1. 1/3 is a fraction between 0 and 1. So this is a vertical shrink. And then by a factor of 1/3. Good. Okay. And again, that's all I need to know is that you recognize it is a vertical shrink, and you can tell me what the factor is. Now, if you were to graph this one, right, again, you would take your basic x squared parabola, you would shrink it vertically, so it would become a fatter parabola, right? It would be open wider than your original x squared graph would. Any questions on the vertical stretches and shrinks now? All right. So let's put it all together, everything we've looked at so far. Okay, so we want to figure out what are all the transformations that are going on here, and then we'll try to sketch this graph. Now, when I see a function that looks like this, the first thing I'm going to do, I'm going to take this value that's in front, and I'm actually going to move it to the end, right? So that's a positive 1. I'm just going to move it to the end as a plus 1, and I'm going to rewrite this as f of x equals negative 2 times x minus 3 squared plus 1. Just because that looks a little more familiar in terms of the transformations that we've looked at. All right, so now let's go down the list and think about everything that we've got. Why wouldn't you add the 1 to the 2? Okay, because remember, order of operations here says we do what's in parentheses, then we do the exponent, then we would do the multiplication, which is the 2, the negative 2 technically, and then we would add the 1, right? So we can't add the 1 in or subtract the 1 and the 2 in this case, because that 2 is technically being multiplied by what's in parentheses first. Does that make sense? Okay. Any other questions about that first step? All right, so now let's think about all the transformations that are going on here, right? And it doesn't matter which one we start with, we just want to list them all out. So what's one transformation that you see here? Okay, we have a shift to the right 3 units. Good, so we start in our parentheses here, right? That minus 3 gives us a horizontal shift to the right 3 units. Good. All right. We also have the plus 1 now that's on the outside of our parentheses. That's going to give us a vertical shift up 1 unit. Okay. What other types of transformations do we have now? Good. We have a reflection, right? So we look at the negative in front here, and we say that's going to give us a reflection over. And remember, when the negative's in front of the entire function like that, that is over the x-axis. Okay. Is there any other type of transformation that's going on this time? There is a vertical stretch, right? So now we look at the 2 that's in front of our parentheses here, and we would say that because 2 is bigger than 1, that's going to give us a vertical stretch by a factor of 2. So in this case, keep in mind, we have to consider the negative sign and the 2 separate from each other, right? Even the negative 2 out front, right? The negative gives us a reflection. The 2 actually gives us the stretch. Okay, yeah. So, we've already described what the negative does, right? That is the reflection piece. So at that point, we can just look at the 2. 2 is bigger than 1, therefore it's going to stretch it vertically. Any questions on finding all those transformations from that function now? And just so you know, right, that's the type of problem I would probably put on a test, right? Because it kind of tests, do you understand all the different types now, right? So you have to find like 3 or 4 different ones within the same function. All right, now our last type of transformation we're going to look at here is a horizontal stretch or shrink. So if instead of having a c value multiplied on the outside of the function, now our c value is on the inside instead. If that c value is bigger than 1, then it's going to shrink horizontally by a factor of 1 over c. So notice here, we're not just using the c value, we're taking the reciprocal of c, putting 1 over c, and that's going to give us the factor that we're shrinking by. If the c value now is a fraction or decimal between 0 and 1, then we're going to have a horizontal stretch by a factor of 1 over c instead. Again, everything on the inside is backwards from what you would expect. So a c value greater than 1 actually shrinks it horizontally, and a c value between 0 and 1, those fractions and decimals, are going to stretch it horizontally instead. Any questions on the horizontal stretch and shrink now? Okay. So let's take a look here, right? And I'm not going to actually do the graph part. If you want to see it, I did it in my video. If you want to go back and look in the course content folder. Okay, but just for the sake of time here, let's just get the actual transformations written down here. So we've got y equals f of 2x. Okay, so what type of transformation are we going to have this time? Okay, it's going to be a shrink by a factor of 1/2. And what type of shrink is it going to be this time? Horizontal. Good. So we have a horizontal shrink by a factor of 1 over c, which is going to be 1/2. So again, that's what I would be looking for right on a test, is describe it as horizontal first of all. Because the c value is bigger than 1, it is a shrink. And then you have to tell me the factor, in this case, is 1 over c, so that's 1/2. Any questions on that one? Okay. Now, what about f of 1/2 x? Perfect, right? So this is going to be horizontal again because it's inside. Because it's a fraction between 0 and 1, that's going to give us a horizontal stretch. And then when we describe our factor now, remember it's the reciprocal of whatever we've got in there. And so we would say it's by a factor of 2 this time. So horizontal stretch by a factor of 2. Any questions on those? All right, so that's where we'll stop for today. We've only got one more example there to finish up next week, and then we'll get into 2.7. Like I said, we should be able to finish up the rest of Chapter 2 next week, which means that our test will be the following week, right? And I'll adjust the homework as we need, so it'll probably be due towards the middle or end of next week is what I'm looking at right now. But again, you've at least got the weekend for sure, okay? Let me know if you've got any questions on that, though. Come see me during student hours whenever you need to. Have a great weekend, and I will see you all on Monday.